Hey everybody. So we're going to talk about measuring the spread of data. So this one gets a little bit complicated in terms of computation, but the good news is you don't really have to do the computation. I'm going to do it once towards the end of this video, but we're going to spend most of our time is understanding what this new measure is going to tell us. Okay, so let's start with a little situation to kind of describe why we might need something like this, right? What do we have so far? We have things like measures of center. If we're trying to describe data with a number, a measure of center, one way we thought about thinking about it is what's the typical data value, right? If you compute a mean or a median in some way, depending on the data, that sort of represents what's a typical kind of, if you picked a piece at random, what number is it going to be near? It's not precisely what it is, but that's often how we think about it. So let's think about something a little bit different. Let's start with this example. Let me share my page. So here's a little bit of a, let's say we have the following situation. We are trying to source some kind of medicine, right? So maybe this medicine has, let's say it's very specific in that we need to give as close as possible to, what did I say, 100 microliter doses. Okay, so we're imagining this as some kind of medicine where you need to be fairly precise, right? Because maybe the reactions to underdosing or overdosing could be severe. And so you need to find somebody who's going to produce this for you where they're going to be able to produce pretty accurate amounts. And so you go to a couple of companies. Let's say there's two companies. I called one of them Acme Medical Company, and I called the other one Beaker Medical Company. Okay, so you go out and you sample several, I think I did 100 samples. Of course, I invented this data. This is a made-up situation. And let's suppose I went out and sampled 100 doses from each of these companies to see what their production was like. Do they actually produce 100 microliter doses, right? Any machine, no matter how high the precision, is going to have some error in it. So not every dose is going to come out absolutely precise, but we need it to be probably within some range, right? So maybe we go and we test 100 samples from AMC and see a mean dose 99.88, not bad. And we go to the Beaker Med Company, and they have an average dosage of 100.24, right? So both of them are within a single microliter. Maybe our tolerance is 1 or 2 microliters, something like that, where we can, you know, if somebody gets a dosage a little bit less or a little bit more, that's fine, but we don't want to go too far away before having disastrous results. Well, that number, the mean, doesn't really tell us everything we need to know. So let's look a little bit closer at this data. So now I've reported to you just the mean here. Let me report to you instead the histogram of data. Okay. So now we're looking at the histogram of these two companies. Okay. So Acme is on top, Beaker is on the bottom, and notice that the scales on the horizontal scales are the same, right? So you can kind of see the corresponding values below each other here, right? The vertical scales are a little bit different, and we'll see why in just a second when we start digging a little bit deeper into this. But what we notice probably immediately upon looking at this is the Acme Medical Company's data is much closer to the center, where the Beaker medical data is spread out a lot further, right? So both of them have averages that are almost precisely 100. They're both very close, but we see very different pictures from the data, right? So for instance, I can look at the range of data, meaning what's the lowest to the highest. With the ACME, right, we're seeing it go between about 96 and 104 versus Beaker is down here at 85 and what is this, about 117 up here, right? So there's a much larger variability, right? This one has a spread of about 8 microliters, whereas this one is about 32 microliters. Right, so there's much more spread, right? And this is also why we have this higher scale on the vertical axis for ACME, because all of that data that is spread out on the sides over here is, we can kind of think, has been pulled in and stacked on top, right? So this is a much taller histogram, right? This one goes up to about 33, it looks like, eyeballing it, whereas the highest ones here are about 10. And so this is a very different kind of picture, even though both of them have averages that are pretty comparable and in the right sort of frame for us, right? And so in this situation, I think it's pretty obvious that we would want to do something with ACME, because this is a much safer choice, right? Where we know our doses are going to be at least closer to the correct amount. Okay, so we want to be able to capture that information in numbers, right? There I showed you a couple of histograms where it was very obvious that one was more spread out than the other. It's not always so obvious, and so sometimes having a number that we can measure, that we can compute and take a look at, will help us make these comparisons that are a little trickier to eyeball. I made that one very obvious. So the number we come up with is something called the standard deviation. So we're going to talk about how to think about that. And like I said, I'm only going to do a computation of it towards the end, okay? So our standard deviation is going to give us let's write this out. We've got standard deviation. So first of all, let's see. There's going to be a couple of different symbols for it. Remember, with the mean, we had a symbol for the sample mean and another symbol for the population mean. We have the same thing here. So the sample standard deviation, we'll usually use the symbol S. And the population standard deviation, we use another Greek letter. This is called a sigma. It's a lowercase sigma. Okay, it kind of looks like a Q that's been rotated 90 degrees counterclockwise. Okay, so, and these are fairly standard. There's some places you might see something a little bit different. So how do we think about this standard deviation? So it's going to be a number. Standard deviation is a number. Okay, it's going to give us a measure of the overall spread of data. The higher the number, the more spread out our data is, okay, in this particular measure. Okay. That's one way to think about it. We can also think of it as the typical distance a piece of data is from the mean. Oh, I forgot the word data in there, or of data. The typical distance a piece of data is from the mean, okay? So when I say typical, it's the same way we kind of think of average as the typical piece of data. If I tell you that, I gave an exam and the average score was 85%, you know that there might be people who got 100% on that, and there might be people who got 20% on that. So it's not typical in that like it necessarily means lots and lots of people got 85 or close to that, but we're trying to capture or summarize all of the data. So this number, the standard deviation, doesn't necessarily mean lots and lots of data is that many units from the mean, but it kind of tells us the average distance. It's another way to think about it. It's not quite the average distance, but that's another way we can think about it. And that's the sense in which I'm using the typical data. One other way I want to think about this standard deviation is it's kind of going to become our measuring stick. Right? Where we can use it to compare data to say, how strange is this piece of data, right? If the typical piece of data is a standard deviation away from the mean, we might ask how many standard deviations away is my piece of data? We'll talk in more detail about that in just a few minutes. But first, let's go back to this example. I computed the standard deviation for these two fictitious companies. And I've got, for Acme, remember this is the one that was much more bunched up, much closer together, less spread out. We had a standard deviation of 1.32. And for the Beaker Medical Company, it was 6.42, right? And I should also say these are all in microliters. The standard deviation is going to have the same units as the mean, which is going to have the same units as the data itself, right? So what we're saying here, for instance, is the typical dosage from Acme Medical Company is 99.88 microliters, and the typical piece of data is about 1 1/3, 1.32 microliters different. So that's kind of the average distance, right? So some pieces are below this, some dosages are above this. Same thing here, and we see there's a much higher average. So the pieces are much more spread out, which is what we saw in those histograms. Okay. So let me look at a little more fictitious data before we look at some other ideas about how we're going to use this. So let's see. There it is. All right, here is some more data in the form of histograms. This is just made up data, so I'm not worried about what it might represent. But one thing interesting in this data is, so all the data we see here have, they all have the same mean of 6, except for this one ended up being something like 5.8 or something very close. So it was a little harder to make it be exactly 6. They all have the same mean. We also might notice that some of this data has the same range, meaning the difference between the highest and the lowest, right? This data here goes from 2 up to 11. This data as well goes from 2 up to 11. So if we just look at how far the top and the bottom are, which is one way to kind of measure how spread out it is, these seem the same. However, looking at these two pieces of data on the left, even though this first column on the far left, this first histogram on the far left has data all the way down here, we see it has less data far away from the mean, right? It's like I took, in fact, this is probably how I did it. I took some of the data sitting here and moved it in towards the center. Took some of the data sitting here and moved it in towards the center. Took some of the data sitting here, moved it in towards the center. So we see data missing compared to this one over here, and more data added in the middle, right? This peak is higher. These two bars next to it are higher. So even though it has the same range, this one on the left is less spread out, right? In some sense, it has some that's far away, but less of it. Okay, and this is reflected in the standard deviations. If you look underneath each of these histograms, we see standard deviations. This one's 1.9. It's very small compared to 2.45, right? This one's, I don't know. This is about a 25% increase in standard deviation. Here we have a set of data that's much more packed together, right? Its smallest piece of data is only at 4, its largest is only at 9. There's lots of it in the middle here, so it has a very small standard deviation, right? And then finally we get this odd-looking data out here where the mean is still in the middle, but none of the data is sitting right on the mean, right? All of the data is far away from it, and so we see the highest standard deviation, right? This piece here has a standard deviation of 3. So this is by far the biggest from these 3 pieces of data. So that's the sense where we think about the standard deviation as capturing, measuring the total spread of all the data, okay? And this is a really good way to do it. You'll see lots and lots and lots of reports of data where they'll report back the mean and the standard deviation, right? So they're telling you about where the middle of the data is and how far you should expect the data to go on either side of it, okay? All right, so let's look at something else now. Let me get some things out of the way here. All right, so we're gonna move into another example. So I found some data on birth weights in a town in Indonesia that I have difficulty saying, Yogyakarta. So I looked up a pronunciation website, so I'm not sure if this sound will come through, but let's try. This is how it's supposed to be pronounced.
Yogyakarta.
Yogyakarta. I'm saying that as close as I can. So in any event, we have data on this town. So let me share with you some of the numbers that I have. So let's see. All right, so in this town, let's suppose, so in this town of Yogyakarta, at 40 weeks, the average birth weight and this is going to be sample data because it's a study that I forget the numbers. I've got it linked, and I'll share that link with you. So I forget the numbers, but it's sample data, right? They don't have data on every single birth. And this is at 40 weeks, and I'm going to use the male examples. The birth weight, the average birth weight, I used M to represent weight in this, just because I have 2 different averages, so I don't want to use X for both of them. The average birth weight was 3184 grams, right? So just so you know, we talked about X bar being a way we can represent the average or the mean. The bar is often used for anything. So I'm using M for the mass and M bar for the average mass, right? Or weight in grams, okay? And let's say we also know the average length at 40 weeks. Here I used L, so L bar is the average. This is going to be 48.8 centimeters, okay? Now, suppose a boy is born and we have a birth weight, so a particular boy, particular birth, we have this birth weight of 2857 grams, and the length of this particular weight of this particular birth is 42.3 centimeters. Okay, so notice in both cases our brand new baby boy is a little bit below the mass and a little bit below the average length, right? So what are we about 300 grams below weight and about 6.5 centimeters below weight, right? So a question you might ask yourself if this is your child is, is this a big deal, right? So it's hard to know. If you're not somebody who has a lot of experience with birth weights, you might not know how is 300 grams a large difference, or is that typical? Same thing with lengths. Is 6 centimeters a large difference, or is that typical? Right? If you were to find out that, you know, baby boys in this region usually come, you know, the majority of them are between 3,000 and 3,300 grams, right? Then you might be a little concerned because this baby is outside of the range where the majority live. On the other hand, if you find that there's a large variability, that they come anywhere between 2,000 and 4,000 grams, then you're sitting right in the middle, and it's not nearly as big a deal. So it's very difficult to understand this data without context. And another question we might ask is, which one of these is more extreme? Is this particular birth more underweight or under length, right? And how do you compare grams to centimeters, right? It's a kind of a nonsensical question to compare grams to centimeters. We can't really do it, right? It's like asking what's more, 2 hours or 7 miles, right? That's a nonsense question to ask, right? So when we're comparing across units, and even sometimes within units, if they're different populations, it's hard to know how to compare them. So the standard deviation can be very useful for this. So let's add some information here. I'm going to add standard deviation information. So the standard deviation for the birth weight, I'll call it S. Remember, that's our symbol for standard deviation. I'm going to put a little m under it to say this is the standard deviation for the mass, the thing that I've been calling m, because I'm going to have 2 standard deviations and I don't want to confuse them. The standard deviation is 410.5. And the standard deviation for the length is 1.8 centimeters. And this is, remember, kilograms. Okay? So again, this comes from some sample data from a study done there that I can link for you when I post all this. So now let's make this comparison using these standard deviations. Notice our particular birth, which is only about 300 grams below the mean, is less than a single standard deviation. One standard deviation is 410 grams, or 410.5 grams, not kilograms. These would be massive babies if they're in kilograms. And our length is, which is about 6 centimeters below the mean, is multiple standard deviations below the mean. Okay, so we're turning this standard deviation into a measuring stick. Okay, so let's focus on birth weight for a moment and do a little diagram of how we can use this thing. So let's see. I think we can fit it all here. Let's do it here so we have all this information at our disposal. I'm just going to draw a little number line. I'm going to put the mean birth weight here. Okay. I'm going to leave units off because this diagram is going to get complicated. We know what the units are, and I just want to, as much as I can, keep it simple. So our birth weight of 2857 is somewhere below this. I'm just going to put it about here. First of all, let's find out how far below this thing is. In other words, what's this distance? So I'll take 2857 minus 3184 is negative 327. Remember, this is grams. Okay. I'm going to put the units on this part for a particular reason we'll see in a moment. So the negative here indicates that it's below weight, right? If my mass had been something larger and I start with the mass of the data I'm interested in, subtract the mean, and this is larger, I'll get a positive number, which tells me it's above. A negative number tells you it's below. So it's nice that we get not only information about how far below, but in what direction. I want to know how many standard deviations this is, okay? So let's think about this. If I told you, if I wanted to measure, let's say I'm looking at new apartments and I want to measure my apartment not in how many feet or meters or something long it is. I want to measure it in lengths of me, right? Because I'm me and I want to know how many of me can I fit in this thing. So maybe I want to know how long is this room end to end if it was me laying down, okay? So to make things simple, I'm not quite 2 meters, but I'm going to use 2 meters as my height to make it simple. Let's say I have a room that's 8 meters long. How many Leos long is it? You take 8 meters divided by the number of meters in each Leo. So 8 meters divided by 2 meters would say that room is 4 Leos long. Right? We're going to do the same thing here. We're going to take the number of grams we have and divide it by how many grams are in a standard deviation to tell me how many standard deviations long this distance is. Okay? So I take negative 327 grams divided by the standard deviation, 410.5 grams. And this gives me negative 0.797. Okay. This is the number of standard deviations. Our piece of data is below the mean. The below is because the negative, right? In other words, it's less than 1. It's about 80% of a standard deviation, just below 80%, 0.797 of a standard deviation, right? I've rounded here, so it's not precise, but up to 3 decimal places. Notice also, this is why I put the units in again. We're dividing grams by grams. There's no units on this thing. It's just a number. Right? It's not some number of things. It's other than standard deviations. It's just counting standard deviations. This is how many of them there are. In other words, there's another way we can think about this. Here's my mean. Standard deviation, the distance it represents, if I went down by 1 standard deviation, I'd be going down to 2,773.5, right? So I'm starting at the mean and going down by 410. I get to here. My distance is just this many standard deviations times the standard deviation. All right, if you take negative 0.797 and multiply it by 410.5, you're going to get negative 327 grams. I rounded, so it's off a little bit because of the rounding, but essentially you get back this number. So that's how many standard deviations this distance represents. Okay? So it's a little bit tricky of a topic. So I know by the end of this video, you might not totally grasp it. We're gonna plow through, and I'll do other examples in other videos. But I want to keep moving with this. There's another idea locked in here in this little understanding, which is this. If I start at the mean, 3184, and I add the distance I got here, right? This distance is negative 0.797 times 410.5. This is in grams, this is in grams, this is just a number, so this is adding grams to grams, or the negative makes it subtracting. I get to my data point. Right? So if I take the mean and I add, so remember what this represents here, how many standard deviations I am from the mean, including the direction, and I multiply it by the standard deviations, I get the total distance I am from the mean in grams. So then I add that number, or in this case subtract because it's negative, to the mean. I land on my data point, right? This number here is going to be the negative 327. If I move 327 below the mean, I get to my data point. So we can use this idea. We're kind of doing two things at once, going in both directions. First, we looked at how many standard deviations away from the mean is my data. And then we see that we can actually use that. If we know that about something, we can use that to reconstruct the piece of data, go the other direction. I know how many standard deviations something is from the mean. I can use the length of the standard deviation to find the actual piece of data. We will be doing this very, very often, and there's a name for this. All right, so let me generalize a little bit of what we just did. So let's start with what I did here. I took a data point. So sorry, let me get this set up a little bit. I took a data point. I want us to still be able to see what we did. All right. I took a data point. I'm just going to call my data X. Oops, I don't mean X bar. I took my data point X and I subtracted the mean, X bar. Okay. And then I took what I got and divided it by the standard deviation. This is something we call a Z-score. Okay, so we'll often just use Z for this. Let me write this on clean paper. I hate that little mistake there. So what we're doing is something called a Z-score. And my formula is just what I did a second ago. I take my data value minus the mean divided by the standard deviation. All right. This one is for the sample. A Z-score for the population looks almost exactly the same. X minus the mu, the mean, divided by the standard deviation for the population, okay? We're gonna do a ton of work with Z-scores later. I introduced it here because it's very tied closely to the standard deviation, so we were doing it. I just wanna tell you the name of it. We'll talk a lot more about these Z-scores. And the second thing we did was reverse this Z-score. And if you follow the algebra, you'll see what happened. But what we said down here is if I start with the mean and I add the Z-score times the standard deviation, I get my data point. Right? One for the sample, one for the population. That's all we did right here. This was our sample mean. This was our Z-score. This was our standard deviation. This was our data. Okay? So we reconstructed the data. And it's just this same formula. Multiply by the standard deviation, add the mean to the other side. You're solving for X. You get this, right? We are going to use both of these. We go in both directions with these quite often. Okay? So we'll come back to these formulas multiple times in the future. Let's finish up our example here. Just for comparison, right? Let's compute. So right here, we have the Z-score for our birth weight. Let's compute a Z-score for our birth length. It is going to be the data, oops, let's call it L, minus the mean divided by the standard deviation, which in this case, our birth length is 42.3 minus the average length of 48.8. This is in centimeters, dividing by the standard deviation. Where did that go? 1.8 centimeters. So we have centimeters minus centimeters gives me centimeters, divided by centimeters gives me no units. And we get a Z-score of negative 3.556, right? So notice the difference in these Z-scores. This length is more than 3. It's 3.5 standard deviations below the mean. This one's not quite 1 below. This is a much more typical weight. This is a much more extreme length right? This birth length is much more extreme than this birth weight. Even though the number of centimeters, it's only 6 centimeters below versus 300 centimeters below. We put the Z-score in some way, puts it in context so we know how we should think about it, right? I didn't know if 300 grams, how to compare that to 6 centimeters, but now I know. This is not very typical at all. This one's pretty typical, right? It's a typical, it's close to the average distance a piece of data is from the mean, okay? Okay, so one last thing to finish. I want to go through the computation of the standard deviation, okay? Now, the standard deviation computation, I'm only going through it because it does give us a little bit of intuition. It is not something you're ever going to have to compute by hand. We will do it with computers. There's a very simple command in Google Sheets. I'll show you after this computation. But I do think the computation is reasonable, reasonable to see once. So here's our formula. There's going to be a lot of, so the population standard deviation, the symbol is sigma. Here's what we're going to do. We're going to take each piece of data, right? So X sub I represents a piece of data. There might be 1,000, there might be 10, but they can be labeled from 1 up to however many there are. We're going to subtract from the mean. Sorry, we're going to subtract the mean from it, right? Remember, this is what we did a second ago. We found out how far away from the mean our piece of data is, okay? Now, the problem is, let's say we have one piece of data. We're going to do this for all of the data and take an average of how far away they are, kind of. The problem is this. If one piece of data is 10 units above the mean and one's 10 units below, if we added those together, right, computing an average, you find out all the distances, add them together, divide by how much data you have. If some are above and some are below, when you add them together, they're going to cancel out. If some are plus 10 and some are minus 10, there's 0, and your average distance would be 0, but it's not, right? One's above, one's below. They're still 10 units away, even if the directions are opposite. So the way we fix that is we square it, okay? That gets rid of the negatives. Then we do this for each piece of data and we add them together. So this is our Greek letter, this is the capital sigma, and it means do this thing for each letter I. So if there's 1,000 pieces of data, 1,000 times we would take the piece of data minus the mean and square it. Then we go to the next piece of data minus the mean, square it, and go through all the data doing that and add those all together. And then we divide by how many data there are. So I'm using N, capital N, for the number of data in the population. Okay. Then our last step is we're going to take the square root of this whole thing. Okay. It sort of corrects for the squaring here. It also keeps our units nice. It means that the standard deviation has the same units as the data. For instance, if our data was in grams like that we did before, we'd have grams minus grams. We'd end up with grams squared. So we take the square root to get rid of that squared. For the sample, we do almost the same thing. All right, there's a couple small differences. The first one I think is pretty straightforward. We're just subtracting the sample mean instead of the population mean. And then instead of dividing by all of the data, this is the weird part, we divide by 1 less than the data. The reason for this is pretty strange, not strange, let's say subtle, difficult to totally comprehend. It's pretty theoretical. But let's just say this. When you take samples, they tend, the deviation tends to be on the smaller side, okay? The sample deviation is a statistic that we're hoping approximates a parameter, right? Remember this idea that we're always trying to approximate parameters. These tend to be smaller. So we subtract 1 subtracting, making the denominator of a fraction smaller makes the whole fraction bigger. And so it kind of corrects for that, okay? We don't need to worry about this idea right now. And then, like I said, you're not even gonna have to memorize this formula. What you do need to know is your computer or calculator that computes it for you will do both. And you need to know, am I looking at sample data or population data, and then choose appropriately which command to give it, okay? All right, when we do it in sheets, there's a standard deviation command, which always does the sample standard deviation, and then there's a standard deviation population command, which does this one, okay? Because the sheets doesn't know what you're looking at, whether it's a sample or not, okay? So we're gonna go through this computation once. I'm gonna compute the standard deviation for a sample with the following data. 22, 99, actually let's do this on a new sheet. I'll keep this nearby, but since this is a big computation, here's our data. 22, 99, 102, 33, 57, 75, 100, 81, 62, 29. Okay, so let me, I've gone through this, but I want to lay it out for you how we would do this. This is also partially so we appreciate never having to do this. All right, so I'm going to start by, I'm going to make a little table. All right, so here's my data. I probably should have just written it in here the first time. Create a little space. We'll come back to those formulas in a moment. 102, 33, 57, 75, 100, 81, 62, 29. Okay. Apparently I can't write straight. So the first column I'm going to create, so then I computed the mean of this data, okay? I did this ahead of time. The mean of this data turns out to be 66, okay? Now, in this column, I'm going to compute what we call the deviation, which is going to be the piece of data minus the sample mean. So just each piece of data minus 66. So I get negative 44, I get 33, I get 36, negative 33, negative 9, 9, 34, 15, negative 4, negative 37. Okay. Right, so this is each distance from the mean. This piece of data is 44 units below. This piece of data is 33 above, 36 above, 33 below, and so on and so on, okay? If you add these data up, right? If I wanted to compute the average distance, what do we typically do? We add up all the scores or the distances and divide by how many we have, but if you add all of these up, all the negatives cancel with all the positives, these sum up to 0, okay? You can do that computation. Pause the video and add those up. You'll see they add up to 0. So this is why we have to compute the deviation squared. So then I just squared each number. 1936, 1089, 1296, 1089, 81, 81, 1156, 225, 16, 13, 69. Okay. All right, so what do we have so far? I've got all of my deviations squared. So the next thing I'm going to do is, I'll use this symbol, add up all this symbol is saying is take each data value minus the mean and square it and then add them all up. So I did this. I took each data value minus the mean, I squared them, then I add them all up. If I add this up, I get 8,338. Then I'm going to divide by n minus 1. and I get 926.4. Okay. And then finally, I take the square root. And in this case, I get 30.4. Okay. This is my standard deviation. Okay. This is the typical distance a piece of data is from the mean. That's not exactly what it means, but it's a really good way to think about it. Okay. The squaring, the n-1 makes that not quite exactly correct, but it's a good enough way to think about it for our purposes. Okay. Again, I'm not really asking you to go through this computation, but what I really want us to see is what we've really done is, in some sense, averaged the distances. Okay. Again, because of the negative stuff, we had to change that a little bit, but that's a good way to think about it. Adding up how far away the things are and dividing by how many there are to get an average or typical distance away from the mean. And the standard deviation tells us it's a measure of the spread of our data. Okay. Last thing I'll leave you with in this video is just this thing here is given a name. We just used the symbol s squared. This is sometimes called this is called the variance. And in certain situations, we use the variance. We won't actually use it too much in any time soon, but it is a term you'll often hear in statistical studies, and so you'll know what that means. It's just the square of the standard deviation, or it's stopping one step short of finishing the computation for the standard deviation. Okay. All right, that is it for this one. Thanks, everybody. I will see you next time.